My name is Victor Kanumbi. This is the Bleach production team.
My name is Daniel Mulandi.
I'm Kandia team.
So our project harmoniously combines the analytical and thermal process, each operating independently from each other, but communicating seamlessly through a classroom IT system. This synergy of devices and processes ensures a streamlined and efficient production process that optimizes resource utilization and enhances the quality of our product.
To empower operators and ensure safety of the system, we've integrated a standard dashboard. This intuitive interface facilitates real-time monitoring, data collection, and operational oversight. Additionally, we've established a customer website that provides transparency and information to everyone. The process begins here at the customer website. The website provides an interface through which the customer can order the bleach and track it through the entire production process. The customer first comes here and fills in their details, including the bleach amount they need. In this case, it's 10. They then place the order, which we receive at the station, and they're provided with a tracking ID of which they can track the production of their bleach. They just need to copy the ID, insert it in the tracker, and once it's tracked, you can see from here the order was received, awaiting production, the cooling, then they will be told when it's dispatched to them. The whole process is then monitored elsewhere using a SCADA dashboard.
So this is the analytical station where the process starts. We first pump in distilled water into the reactor tank. Then the distilled water will be used to reduce the concentration of the calcium hypochlorite, which will be pumped in by the peristaltic pump. We have a pump here and a pH sensor to monitor the regulation. Once the required set point has been reached, this solution will be transferred into the thermal station for cooling. And once it's in the thermal station, it will be pumped through a centrifugal pump and circulate in the system, whereby a chiller will be cooling the solution to the required set point also. So on the SCADA, the operator is able to navigate to the processing station and start the process. And as you can see, the input pump is turned on the SCADA and it starts pumping in the distilled water. So the filling takes quite some time to fill, but once it reaches the required point, you can see the whole system starts and the pump starts rotating, and the pump starts rotating according to the logic of the PID. It starts pumping in the concentrated calcium hypochlorite solution, which will be distilled until we reach the required set point. So this takes quite some time until the regulated pH has been reached. So once the required pH has been reached, our set point, the solution starts transferring from the analytical station to the thermal station. So once the transfer is done, the solution starts circulating through the chiller where it's being cooled.
This is the tier program for the bleach production system. We're using two S71200 PLCs. And let's start with the analytical station. So in the analytical system is where the bleach production is actually taking place, and we're using a pH sensor to monitor the concentration of the calcium hypochlorite. So in the first network, we have called the function block where we are normalizing and scaling the
values from the page sensors. Page sensor, it's the easy one. And in the second network is where we have written the program for the actual production. So it starts with resetting from the previous cycle, and then we start the water pump that is pumping clean water into the process tank. And then once it has reached the right value, it resets the water pump, and then we open the inlet and outlet solenoids for the process tank, and then we start the circulation pump, and then start the peristaltic pump and the agitator. The peristaltic pump we are using to pump the concentrated calcium hypochlorite into the process tank, and we are controlling its speed using a PID controller that we have made. And then once the pH value has been achieved, we stop the circulation and we transfer the process fluid to the thermal station for cooling. And on the thermal system, the ultrasonic at the thermal process tank will tell us when it has reached the maximum value, and then we will reset all the outputs and prepare for the next cycle. In the thermal system, we in the main OB, we have called three function blocks. The first one is the temperature sensor processing, whereby we are normalizing and scaling the values from the temperature sensor. And then in the second network, we have the bleach cooling function block, which contains all the processes for the thermal cooling in the thermal processing station. So we start by sending in the first network, it's sending data to the analytical station, and it is also resetting the thermal station from the previous cycle, and it's sending the data from the ultrasonic sensor to tell the analytical station that the process fluid has flowed from the analytical to the thermal station. And once this is done, once the process fluid has been received, we start the centrifugal pump, that is the process pump that running the process fluid throughout the system, and we also start the chiller. We then start the hot water centrifugal pump to pump the hot water through its own hot water system, and then we control the the temperature of the process fluid. We have a PID here, and we are controlling the flow rate of the hot water. So once the chiller is cooled the process water and cooled it to below 16, the PID will start the flow of the hot water to the hot water heat exchanger to warm it up a bit and ensure that it remains within the range. So this is what you have flow flow rate actuator processing function block. So in this function block, we are normalizing and scaling the values from the flow rate sensor. We are, we then stop the cycle once the temperature has been achieved. We reset everything from the process fluid to the chiller to the hot water centrifugal pump, and then we indicate that the cooling has finished to the operator.
To optimize communication and improve on the efficiency of our system, we developed an industrial IoT system, which, after careful consideration, we chose MQTT as our primary communication protocol. This decision is rooted in its exceptional attributes such as low latency, lightweight code base, and its open source nature. The utilization of MQTT not only ensures swift and responsive communication, but also provides the advantages of an open source framework, for which, in our case, is the EPL license, alleviating concerns about licensing restrictions. Our system core is powered by an MQTT broker running on a Linux host. This pivotal element orchestrates communication among diverse devices and processes. To ensure optimal performance, we opted for the MQTT broker, which is running on a Mosquito broker, which is an open source software implementing a MQTT protocol version 3.1. As you can see from the flowchart, MQTT broker is at the center of all the communication happening in our project. Um, the rest of the devices and processes are connected to the broker to so as to exchange information effectively on the background. So here we have our Mosquito broker running on a Linux device. It's running on the background and it's attached to the port 1833. We also have the MQTT Explorer, which is used to browse through the MQTT messages being sent by the different devices and processes. And also at the top we have the Madrid server, which is used to host our SCADA systems. And also here we have the web page web app, which is used to serve the web pages for the client to order their product.